ahorita me consta que no. Good afternoon, everyone. Today we're gonna start chapter 2. Chapter 1 is not done yet. We still have, I think, 1.8, 1.9, which are very important. But I usually do them after I do 2.1, 2.2, 2.3, because they will make more sense to the student usually. So today we're gonna do section 2.1, one of the easiest section in the course, and very basic, very important also. So matrix operation. So we're gonna do now, start doing algebra on matrices. So we introduced matrices as a rectangular array of numbers that we definitely needed it to solve system and to write system in a more compact way as a matrix equation. Today we're going to start operating on matrices. We're going to add them, we're going to multiply them, we're going to transpose them, and eventually we're going to invert them. So first, the idea is how people write a matrix in its general format. So suppose A is a M by N matrix. Remember, M by N, it means that this is the number of rows and this is the number of columns. Okay, and if I'm writing a matrix in an abstract format, we usually write it like this. So we have to be familiar with that. Okay, so I will put the solution, sorry, I will interrupt. Grace, I will put the solution on right space. So I will not review it in class. I usually review it at the end of the semester as a preparation for your final exam, but the solutions will definitely be posted, okay? So usually we write it like this. A1, 1, to denote the term in the first row, first column, and then 1, 2, so that's how we usually write it, first row, second column, and etc. Since I have n column, it's going to be A1n. And then second row, first column, second row, second column, second row, the nth column, and we keep going. Since I have m row, that's going to be M1, M2, and finally Mn. So that's how we write the matrix in its abstract format. So Aij, that's the entry in. The first one tells me the row, ith row. The second tells me the column, second column. Okay, so that's really how it works. And a lot of time you would write A equal Aij instead for it. So to tell you that the entries of the matrix A are the Aij. And we sometimes put also I, which is the row going to M and J from 1 all the way to N. So that's in a whole how we represent a matrix. Now, sum of matrices. We're going to add matrices and multiply them. Sum of matrices and scalar multiple of a matrix. Okay. Let us say we have two matrices. And let A and B be two matrices that have, that's important, the same number of rows and the same number of rows and the same number of columns. So the same number of rows and the same number of columns. Okay, so we have two matrices. They have same number of rows, same number of columns. And then, so let us say A is, we call its entries Aij, and B, we call its entries Bij. Now we can form a third matrix. It's A plus B. Okay, and we're going to add them in the most natural way. What do I mean by adding them in the most natural way? It means A plus B is a new matrix whose entries are Aij plus Bij. Okay, and what's crucial that for this to make sense, A and B have to have the same number of rows and the same number of columns. Otherwise, this definition makes no sense whatsoever. And then we're going to scale a matrix. What do I mean? We're going to take a matrix, and that C be a scalar. It means a number, no more, no less. C is a scalar. So we're going to define a new matrix. Suppose we have A. What does it mean to multiply a matrix by a scalar? It means to multiply every entry by the scalar. So multiplying a matrix, it means multiplying every entry by the same scalar. So two very quick and application to that. So for example, suppose A, so the question is evaluate if defined. So let us say, I don't know, let us say, I will choose easy numbers. So 1, 2, 4, 5, B to be, let us say 1, 2, 3, 4. And C is 1, 2, 3, 4, 5, 6. And the question is to evaluate if defined. So one is the sum defined. We can add matrices as long as they have the same number of rows and the same number of columns. If they don't have that, we cannot add matrices. So that's how the sum is defined. So A plus B is it defined. All right, I always look at A is 2 by 2. So that's 2 by 2. B is 2 by 2. So there is no issue with them. We can add them. So this is nothing more than this plus that. And adding them, it means we add term by term. Term by term. Means 1 plus 1, 2, 2 plus 2, 4, 4 plus 3, 7, 5 plus 4, 9. That's what it means to add two matrices. Now scaling them, suppose I take minus 2 times A, minus 2 times A, it means multiply every entry by the scalar. It means every entry, minus 2, minus 4, minus 8, minus 10. So we can always scale matrix. There is no restriction on that. Now what about A plus C? Is this defined? Okay, whenever there is a sum, I have to go after my matrix. Do they have the same number of rows and columns? If I look at this, it has 2 rows, but it has 3 columns. Definitely not defined. So we have to be very careful. We cannot just add matrices the way we want. We have to make sure things work. So they're not defined because the number of columns of A are different than the number of columns in the matrix C. Now addition have, whenever we introduce an algebraic operation, we ask ourselves, are the basic rule of addition work? So what do I mean? So basic properties of addition, the one that we want them to happen. So first, that if you add A to B, as long as the sum is defined, it's the same thing as adding B to A. It makes sense because we're just adding terms. Whether you add 1 4 to 3 or you add 3 to 4, you're really not doing much of anything. So that's the first property. And if you guys remember your basic middle school math, this was called the commutative property. It means A plus B is B plus A. Another property is, suppose A m by n. I take A and I'd add it to the 0 made equal to A. But here we have to be careful. What do I mean by 0 in here? So every time you write something, you have to know what you're writing. What do I mean by 0 in here? That's a matrix. What I mean by that is the 0 matrix. Means I'm going to put m by n 0 matrix. It means that's the matrix whose entries are all 0. It's not the 0 number. It's absolute nonsense. I cannot add 0 to a matrix. I add a matrix to a matrix. So that's a matrix where all the entries are 0. And it has n column and m row. Okay, so we have to be very careful with our 0. No matter how simple this is, we have to be very careful with that. Another property, basic property, is that if C is a scalar, and I'm multiplying it by, let's say, A plus B, I can actually distribute the scalar. Okay, very simple property. And the other thing is that, sorry, that's it. Okay, those are the basic algebraic property that you like them to work, and because the addition is so simple, they go through. Part 2 is how to multiply matrices. So addition is simple. Now we're gonna do product of matrices. Okay, so product of matrices. And I will elaborate how to multiply matrices by an example, not by the general theory. So I'm going to take 2 matrices, and by example, we're going to show how to multiply them. So let me take the following. Maybe I should use pencil because I do stupid arithmetical mistake. So let me take this matrix. 1, 2, 4, 0, and minus 1, 2. That's my matrix A. And I'm going to multiply it by another matrix B. And B, let us say it's a 4, minus 1, it's a 4, and a 2, and a 3, and a 5. Okay, so we multiply 2 matrices. We're going to create a new matrix. We're going to call it C. Okay, and the question is how we multiply matrices. Okay, let's see how it works. We start with the first row of A and the first column of B. And we do the following. 1 times 4, row, column, plus 2 times 2. That will be my first term. First row, first column will give me the first term. Then, first row, second column. So first row, second column, I will do the first one fairly slowly. So it's the first row, first column. Sorry, first row, second column, plus 2 times 3. And I keep going. First row, last column, means 1 times 4, 1 times 4, plus 2 times 5. So this will give me 14. Okay, so first row, first column, first row, second column, first row, third column. And then I move to the second row. And I repeat the same process. Second row, first column, 4 times 4, give me 16. Second row, second column, minus 4. So it's not intuitive. It's not intuitive. Second row, third column, 4 times 4 would give me 16. And then I move. Third row, third row, first column, and then repeat the process. -4 plus 4, it's gonna give me a 0. Third row, second column, give me -1, that's a 1. 1 plus 6, that's a 7. And finally, third row, third column, -4 plus 10, which is gonna give me a 6. Okay, so that's how we multiply matrices. It's not term by term at all. It has nothing to do with that. No, absolutely. We're gonna talk about that in 1 second, Valerio. Absolutely, it's important. So row, column, row, column, row, column. I'm done with the first row. Then you want to move to the second row. Row, column, row, column, row, column. The third row, row, column, row, column, row, column. That's how we multiply matrices. So let me give you another example. And okay, so let me take the following matrix A. So that's example 1. Example 2. Okay, I'm going to take the following matrix. 1, -1, 0. And 2, 4, 1. And 3, 3, 2. That's my matrix A. And I'm going to multiply it by the following. So B, so instead of writing numbers, I'm just going to write letters. A, B, C, D, E, F, G, H, I, whatever, K, L, M. I mean, it doesn't matter, numbers or letters. So, and this is my B. And I'm going to multiply them. And I'm going to get a matrix C. Okay. And definitely, I'm not going to multiply them, but I'm going to ask you a very simple question. I want you to find the following for me. So C has entries. I want you to find the term of C in the first row and the second column. Because I want to find specific entries in C. I don't want to find all of C because we don't need to. So how can I get C1, 2? If anybody figured it out, just let me know and I can write it down for you. So I want the one in the first row, the second column. I want this one. So this one, this is first. I want that one. Who can tell me exactly this entry? Anybody? On chat, please. How will I get exactly this entry? So I want the entry first row, second column. So try to remember, how do we multiply? Row, column, row, column. So what should go here? What should I multiply to get that?
The first row of A. The second column of B.
Second column of B. Exactly. That's how I'm going to get it. So what's going to be? It's going to be equal D minus E plus 0. Okay, I'll give you another one. I want you to get me the following. I want the entry in the third row. Now I want all of you to be able to give it to me. And I don't know, in the first column. So I want the third row and the first column. How do we get this particular entry? What should we multiply by what? And then I'll give you one more, and then the idea should become clear. Okay, write your answer on chat if or speak up, whatever you guys want. But please, I want answers. So I want this one here. How shall I get that?
Would it be 3A plus 3B plus 2C?
3A plus 3B plus 2C. Absolutely correct. Third row, first column. Finally, C33. How are we gonna get that? I want the term in the third row and the third column. I'm gonna get it from the third row and the third column. Those will give me the C33. So it's gonna give me 3G.
3G plus 3H plus 2I.
Okay, so that's how I multiply matrices. Okay, so it's a long process, but it's not a hard process. Now, let me go back to Valeria's question, which is the following. The question is, under what condition can we multiply matrices? Okay, so when is the product defined? Okay. For some, we add matrices as long as they have the same number of rows and the same number of columns. Now, what about multiplication? So suppose A is m by n, m rows and columns, and let us see B r by s, r rows and s columns. So when is the product defined? Okay, let's go back here. How is it defined? For this to make sense, the number of columns here and the number of rows have to match. Otherwise, row column doesn't really make sense. I should have as many columns here as I have rows here. So the product makes sense. I have A minus B plus C. Here, again, for this to make sense, the number of columns of A should coincide with the number of rows of B. Otherwise, the multiplication doesn't make sense. I cannot make up anything. So if I have one extra term here and I don't make up. I need the number of columns here to coincide with the number of rows of B. So if I have matrices, A times B, if defined, is the number of columns of A equal, it's the same as equal the number of rows of B. So that's the condition for the product to define. So if A is m by n and B r by s, so this tells me the following. A times B is defined if n, the number of columns, equal r. So that's the condition under which the product is defined. That's when we can multiply two matrices. Now, if I know the size of A, I know the size of B, and A times B makes sense. What's the size of A times B? So when I say size, it means what's the number of rows and what's the number of columns of A times B. So my second question is the following. Okay, so suppose A is, so it's the same idea. Suppose A is m by n. And B, I want AB to be defined. I want this to make sense. For this to make sense, B has to be n by s. Otherwise, it doesn't make sense. So if A is m by n, for the product to make sense, B should have the same number of rows as the column. So it means that should be picked. That's the picture. Those have to be the same for the product is defined. But the question that A times B is a matrix, but what size matrix is that? Okay, let's go back to the product and find this out. Okay. Let's go back to this product. A times B, how many rows should it have? Where did the rows come from? They came from the rows of A. If I have 3 rows here, the product is going to have 3 rows. If I have 4 rows here, the product's going to have 4 rows. So the number of rows should be the same as the number of rows in A. Okay. But what about the column? Where are the columns coming from? The columns are coming from the columns of B, because I take the first row times first column, first row, second column, third column, fourth column. So the number of columns of the A times B is going to be exactly the number of columns of B, which is a 4 in this case, which is going to be 3 times 4. And that's happened also in the first one. The number of columns depended on B. The number of rows depends on A. And this will basically bring up the following. If A is m by n, B m by s, then the product is actually, the easiest way to remember it is m by s, is m by s, the number of rows of A and the number of columns of B. Okay. So let us spend 2 minutes practicing these ideas a little bit. So my question is, evaluate if defined. Okay. All right. So let's take a couple of examples. Now let me take A to B. 1, 2, 3, 4, 5, 6. It's my A. And I'm going to take B to B, let us say A, B, C. Let's note one thing. Note that B is a vector in R3. Okay, so it's nothing more than a vector in R3 because it's not, it's a 3 by 1 matrix. So it's consists of a list of 3 numbers. And let me take C to be 4, 5, 1. And let us say 1, -1, 3. Okay, so these are my matrices. And now the question, I'm going to give you a bunch of product and you have to tell me defined or not defined. So let us start. A times B. Defined or not defined? What do you think? Quickly. Defined. All right, let's see if Matthew is correct. A is 2 by 3 and B is 3 by 1. Those are absolutely equal. So the number of row, the column corresponds. So this is defined. And actually, it's not only that. I know what size matrix I should get. And it's going to be a 2 by 1 matrix. But that's actually very helpful because I know what I should get when I multiply them. So now evaluate if defined. So let us multiply them. And that should tell you that, you know, it's like a matrix times a vector that we actually know how to do. This definitely coincides with the row column definition of a matrix and a vector. So it's A plus 2B plus 3C. And this is in R2 because we're going to get a 2 by 1 matrix. Means I'm going to get just a vector in R2 in here. And this would give me 4A plus 5B plus 6. Definitely a matrix in a vector in R2. All right, so let us do 2 more. Suppose I tell you BA. Define, not defined. Watch carefully what I did. Define, not defined. Analyze it. No. What's B? B is 3 by 1. What's A? 2 by 3. Definitely not equal. So the number of columns of A, sorry, the number of columns of B is different than the number of rows of A. So BA is not defined. Okay, so watch very carefully here. Multiplication is going to be a little tricky because A times B makes sense. B times A absolutely doesn't make sense. So when I multiply matrices, the order in which I'm multiplying them is absolutely crucial. And like sum, as I said, in sum, A plus B, B plus A is actually the same thing, but multiplication, it definitely doesn't carry this property over. One could be defined and doesn't the other. Changing the order can create a matrix that's not defined at all. So the order in which we multiply will play, it's absolutely crucial for matrices. Okay, let's try one more and then we change. I mean, that will be done. A times C, defined, not defined, very quickly. So, okay, A is 2 by 3 and C is 3 by 2. So those are equal, definitely defined, not only defined, it's defined and it's a 2 by 2 matrix. It's very important to know the size of the resulting matrix because at least now I know that if I multiply them, I know what to get. I have to get a 2 by 2 matrix. So we will not finish the multiplication, but at least I'll start it. So 1, 2, 3, 4, 5, 6. And the C I took was 4, 5, 1. And 1 minus 1, 3. So now when I multiply them, I know what I'm getting. I know that this has to be 2 by 2. And it's a good guideline. It really helped me at least to know that I got the right size. And now how I multiply them? Row, column. 4 plus 10, 14. 14 plus 3, that's a 17. I got that. 1 minus 2 minus 1. Minus 1 plus 9, that's an 8. That's a 16, that's 25, and that's 6. That should give me something like that. And that's a 4 minus 5, that's a minus 1 plus 18, 17. Okay, so that's really how we multiply matrices. Now, we defined an operation called multiplication. And we defined an operation called addition. We talked about the property of addition. Now we're going to talk about the property of multiplication. What kind of properties does it have? Please, if I move on and you need more time, let me know. Okay, so property of multiplication. So properties of multiplication. So first, already we have one issue that we have to be careful with which matrices can we multiply. We had another issue that AB can make sense, but BA does not make sense. So we cannot, the order in which we multiply is absolutely crucial. So those are already things that we point them out. But there are other properties that follows. But before this, I need to introduce something called the identity matrix. Okay, so what's the identity matrix? All right, the 2 by 2 identity matrix. The 2 by 2 identity matrix, it's I2. That's called the 2 by 2 identity matrix. It's defined as follows. It's the matrix which is 1 along the diagonal and 0 everywhere else. So 1 along the diagonal and 0 everywhere else. I stand for the identity, 2 stand for the size, that's a 2 by 2. And by the same idea, we can talk about the 3 by 3 identity matrix, which is a 3 by 3 matrix. So that's, and it's 1 along the diagonal, it's 0 everywhere else. So this is what we mean by the identity matrix. So in general, IN is the matrix, which is n by n. It's 1 everywhere here, 0 everywhere else. Okay, so that's the identity matrix. Now, property of the multiplication. What do I mean by that? What I mean is that when we, in regular numbers, like, you know, the numbers 1, 2, 3, there are some properties. Like, for example, 2 times 3 times 6 is the same thing as 2 times 3 times 6. Okay, and because of this reason, when we multiply numbers, sometimes we forget about the parentheses and we write them like that. Because regardless how they put the parentheses, it's the same number. And if you remember this property, do you guys remember the name of this property for numbers? Anybody?
Distributive?
No.
Oh yeah, associative.
That's the associative property. Now matrices carry this property. So what do I mean? Suppose I have a matrix A, and now I'm assuming everything defined. So I'm assuming everything I'm writing makes sense. Suppose I have a matrix A and I'm multiplying it by the product of two matrices. And as I said, I assume everything makes sense. I can move the parentheses around. It means if I realize that multiplying A by B is easier first, this tells me that we can move parentheses around times C. So this is called the associative property. Okay, so that's basically moving parentheses around. If we realize that, suppose I want to multiply those matrices, but then I look at them and said, you know, A times B is easier. This tells me you can move parentheses. I'm not changing anything, I'm just moving parentheses around. Property 2. And that's the distributive property. Means how we can distribute matrices with respect to addition. Again, I'm assuming everything is defined. Suppose it take a matrix A and multiply it by the sum of two matrices. Again, I repeat here, I assume things defined. I can distribute. So it's A times B plus A times C. So I can distribute the addition. And this is called left distributivity. Okay, left distributive. So I'm distributing from the left. And then I can distribute from the right. So suppose I have A plus B times C is also A times C. I can also distribute plus B times C. And this is called the right distributivity. Okay, so I can distribute addition with respect to multiplication. Now let me make here a note a little bit that, I mean, why we talking about left and right, there is a reason, because this is not the same thing as that. Because as we realized a minute ago, the order matters in which multiply. I will emphasize this a second time. The order matters. So A times B plus C is not B plus C times A. So here I'm distributing from the left, A times B plus A times C. It's not B times A, which is wrong. It's A times B, A times C. It's not B times A plus C times A. I can't do that because multiplication order really matter in which we multiply. Okay. Now, why this is important for us? Okay, for the same reason. I mean, you're operating on matrices. You should be able to know that if you have A times B plus A times C, you can factor out the A from the left. You can factor out here the C from the right. But what you can't do, if you have AC plus BA, then you cannot factor anything in this case, because the BA and the AB are not the same. So that's what you can't do. So you have to have C, C, you can factor, A, you can factor. That's why we break those into two different situations. The last important property also from multiplication is the following. Suppose I take a matrix here, I don't know, A, B, C, D, E, F. And I'm going to multiply it by the identity matrix. Now I watch the, we have 3 columns, 3 rows. I'm safe. My multiplication is correct. Now let us multiply. Let's see what should we get. So that's a 2 by 3. I am multiplying it by a 3 by 3. So those matches. So the result has to be 2 by 3. So I know here I'm going to have a 2 by 3 matrix. It means I'm going to have 2 rows and 3 columns. So let us multiply them. A times that. ABC times this column give me 0, B. This time that 0, 0, C. D, 0, E, 0, 0, F. So if I take the matrix A, multiply by the identity matrix, I'm getting the matrix A back. So those are absolutely the same. That's really what the word identity means. It's the one for numbers. The identity for matrices is the one for numbers. Every number times 1, it gives you a 2. A matrix times the identity will give you the matrix back. So that's what played the role of 1 for matrices. But now I have to write this very carefully here. Suppose A, M by N matrix. So if I take A, and this is M by N, if I multiply it by IN, I get A back. So I have to really be careful with this identity. Now I can do the same from the other side. You can check that, but here it has to be M times A, which will give me A. So when I multiply even by the identity, I have to make sure that my, my product is actually a well-defined multiplication. Now, I'm going to comment a small cases for, so let me see this distributivity property. So like, it's not this, I will call this special case, but it's actually not much of a special case. So special case, suppose I have U and V like vectors in Rn and A M by N matrix. Remember that vectors in Rn are n by 1 matrices. Vector in Rn are n by 1 matrices. So if I take A and I multiply it by U plus V, the sum of 2 vectors, then this property tells me is that you can split it. So it's A times U plus A times V. Okay, so it's nice to see that if my matrices are particular, means if my matrices are vectors, so the way we translate this, that I'm multiplying A by the sum of 2 vectors, I can basically split. So it's A times U plus A times V. Also, if I multiply A by any combination of that, so it's A times 2U plus A times V. So that's really, we can split that. Now, scalars could be moved around. So it's A times U plus A times V. All right, so I apply, by looking at vectors as column matrices, we can use all the properties of matrices and apply them exactly to vectors. Okay. Now, we defined, as I said, an operation on matrices, and I talked about what properties work. So the associative property, distributive property, and what we call here the identity property, those are work. But there are properties that we want them to work, but they don't. So the book actually called those as warning. And let me see what the book is talking about. Okay, the first thing is the following, is that multiplication is not commutative. What does it mean? It means AB is not necessarily BA. Sometimes it is. So in general, sometimes they are equal, but in general, they are not equal. It means multiplication is not commutative. And this plays a role in matrices. Make them a little bit different than, so multiplication is not commutative. Okay, so the order, important. Now, the example I gave you so far was example that one of them is defined and the other one is not defined. But even if both make sense, still multiplication is not necessarily commutative. We cannot switch the order of the multiplication when we work with matrices. So, example, suppose I take A to be, I don't know, actually almost if you choose any matrices by random, you will have, this will fail. So suppose I take this to be 1, 2, 3, 4, and B, I don't know, something simple. Okay, now AB is defined because it's 2 by 2 by 2, and the other one, and BA is defined. So we don't have problem with them, but let's see, if we compute A times B, and let us compute B times A. So 1, 2, 3, 4, 0, 1, 1, 0. So I will get 2. I will get 1. I will get 4. And I will get 3. Now, if I multiply them here, 0, 1, 1, 0, 1, 2, 3, 4, 0, 3. I don't need to finish. They are two different matrices. Because matrices are equal if they have the same size and if they have the same entries. If they change by an entry, the matrices are not equal. So that's the first property that we have to be careful with. We cannot, the order matter. The order is crucial in matrices. 2, something that numbers have, but matrices don't carry this property. So let me ask you the following questions. Suppose you're multiplying two numbers, multiplying them, and you get 0. How can this happen? Numbers, regular numbers. If you multiply them, you get 0. What can you say in this case? How can the product of two numbers be 0? Either this 0 or C is 0. There is no other way out. So when you multiply two numbers, the only way that could be 0 if one of them is 0. This property fails for matrices. It means we can have two matrices, both of them not 0, but when you multiply them, you get the 0 matrix. So the second property of matrices, that's not what we want, but that's how it works. So in general, if you have two matrices, if the product is 0, remember 0, that's the 0 matrix. That's the 0 matrix, not the 0 number, that's the 0 matrix. Then we cannot conclude, in general, we can't conclude that A is 0 or B is 0. So we can multiply two matrices, neither one is a 0 matrix, but the product could be 0. So I'll give an example for that. So let us see. And I'll let you check it. Usually student gives me examples because those are not hard. Suppose I take 1, 0, 0, 0, something simple. And I take 1, 0, 1, 2. Okay, and I multiply them. A times B. Okay, I get, no, 1 plus 0, I don't want that. I want 0 here. Okay, so let's say A times B, 0, 0, 0, 0, 0, 0, 0, 0. So the product is 0. A is not the 0 matrix. B is not the zero matrix. All right, so again, if you multiply two matrices, you get a zero matrix. You cannot tell me that one of them is zero. This is another property of matrices that's going to fail. Now, what else failed for matrices? I'll take you to numbers, and then I'll carry you to matrices. In numbers, suppose you have the following. I tell you A is different from 0, and AC equal AB. Okay, what can you say immediately? Back to you. You're working with numbers. A is not 0, and you get AC equal AB. What can you say about B and C? They're equal, right? You can say, okay, A is different from B. You can divide by A, both sides, because it's non-zero. And then you get C equal to B. So basically, you simplify by A. Okay? This doesn't work for matrices. In other words, in matrices, if you have A times B equal A times C, you cannot scratch. This is absolutely doesn't work for matrices. So what's the situation? So the situation is the following, and that will be one of your problems. I will not give an example. So 3 is the following. If AB equal to A times C, so it's the same matrix, we cannot conclude that B is equal to C. Okay, so we cannot scratch matrices like we do for numbers. This operation does not exist for matrices. We cannot simplify matrices this way. So those are properties. So algebra of matrices definitely changes from the algebra of regular number. It has some of the nice properties of regular numbers, but it has others that don't work. And the most important one is the order. Whether the order is not important for numbers, the order play a crucial role for matrices. And this is really going to give us difficulties. Okay. And I'll make a comment about that before we move on. For numbers, we have 3 operations, basically: addition and subtraction, which are the same operation. And then we have multiplication for numbers, and we have divisions. We don't have divisions in matrices. This operation is not defined. We multiply matrices, we add them, subtract them, but we don't divide them. And the reason there is no such a thing as division is because the order of matrices is not defined. So let me write, we do not divide matrices, and that's very, very important. So we do not divide matrices. And let me explain why. Okay, we do not, I'll give you an idea why we don't divide matrices. It means something like A over B. Usually I tell the student, if I see you writing something like this, I take point away. I mean, this doesn't exist. And let's see why, not because I said so. Okay, if I take 6 divided by 3, okay, it's equal to 2. Because what does it mean 6 divided by 3? It means how many 3's are in 6? There are 2 3's. So this is because 6 is 2 times 3. So the reason this is here, because division is actually multiplication. So when I'm asking you what's 6 divided by 3, I'm asking you what is the number when you multiply it by 2, you get 6. So now, what shall I give? What meaning shall I give for that? A over B equal to C. What shall I mean by that? Do I mean by that A equal C times B or B times C? Those are different. So for this reason, division cannot be defined. I cannot give you an answer for division. We cannot define division. Okay. All right. Now we're going to talk about, so we did the operation on matrices. Now we're going to talk about something called the transpose of a matrix. So transpose of a matrix. So what's the transpose of a matrix? So suppose we have a matrix A. Let A be a M by N matrix, M rows and column. Okay, then the transpose of A, D, transpose of A, denoted by A with a T in here. T stands for transpose. So transpose by is the N by M matrix, N by M. So the original is M by N. The transpose is flipping them, whose columns are the rows of A. Whose columns are the rows of A. So what am I talking about? What is the A transpose? Okay. Suppose A is the following matrix. So whatever, 1, 3, 4, 5, 6, 7. That will do. That's my A. And that's a 3 by 2 matrix. The transpose is the matrix whose columns are the rows of A. Means it's the following. Sorry. The row of A become the column. The row of A become the column. The row of A become the column. So that's what the transpose is. So it's the matrix where you take the rows, make them column, row, make column, the row, make column. So that's the A transpose. So let us a little bit, 2 examples where we're gonna compute a little bit with it. So my question again is evaluate if defined. So evaluate if defined. Okay, so let us see. Suppose I take A to be the following matrix. 1, 3, 4, 5, 6, 7. So I won't change that. And I want to take U, a vector. So let us say in R2, minus 2, 3. And I'm going to take V to be another vector. I don't have to, but I think vectors are nice to work with. 3 and 2. Okay. And now I'm going to give you a bunch of matrices, a bunch of product, and the question are they defined. Okay, A times U, is it defined? Right. I always analyze before I start multiplying. A is a 3 by 2. This is a 2 by 1. Definitely defined, and the result is a 3 by 1 matrix. So we've done this before, so I will not do that. Okay, so that's easy. Okay, now let's do another one. What about A transpose U? Again, is this defined? Yes or no? Let's say A transpose. A transpose is 2 by 3. U, it doesn't change, 2 by 1. Those are different from each other, not defined. Okay. All right, now let us just work with vector. Let me take the following. Which one I want? I want V transpose U. Okay, let us analyze this. What is V transpose? So I'll write here V again so we can see it. My V was 3, 2. And my U was minus 2, 3. So what's V transpose? V is, for us, it's a matrix, and it's a 2 by 1 matrix. So what's V transpose? that's a column matrix. V transpose is actually the column turned into the row. So that's a 1 by 2 matrix, 1 by 2. So this is a 1 by 2. What's U? U hasn't changed. It's always a 2 by 1. Now, is it defined? Absolutely so. When we multiply them, what should we get? It's a 1 by 1 matrix. It means a number, which is a scalar. Now let us perform the multiplication. So what's V transpose? That's 3, that's a 2. And I multiply it by -2 and 3. And this should give me what? 3 times -2. So I'm going to start opening the matrix, but then, yeah, I don't need to. 3 times -2, so it's a row, it's a column. We're going to get one number. We're going to get -6 plus, okay, 3 times 2, which is equal, in this problem, happened to be equal to 0. Okay, so V transpose U is actually nothing more than a scalar. So it's this times that plus this times this. Now, if you, most of you are taking 261 now, most of you had vectors. What does this represent in terms of vectors? So I'm taking the first entry, times it by the first entry of U, plus second entry of V, times it by the second entry of U. Does this remind you anything in terms of operation on vectors? Anyone? Your calculus 3 teacher will not be happy if you don't know the answer. What does this remind you? No. What does this remind you? It has nothing to do with Ax equal to b. I want you to think in terms of vectors. What does this remind you of? The first component times this component. That should remind you absolutely the dot product of the two vectors. Okay, so the transposing V transpose times U, and this is a concept that you definitely will use in your physics course or whatever, is actually nothing more than the dot product of the two vectors. That's really the operation you are performing right there. Okay, now the last one. So now this one is again to practice. Suppose I switch it around. I take U times V transpose, and will this be a defined operation or not? Okay, U is a 2 by 1. V transpose is a 1 by 2 because we just analyzed those. So definitely equal, and thus the result should be a 2 by 2 matrix. So at least this will give me an idea when I'm going to multiply those matrices, what I'm going to end up with. So let's see that. So U is -2, 3. And V transpose 3 and 2. And I need to get a 2 by 2. So let us multiply them. Row, column, row, column, row, column, row, column. And this is a 2 by 2. All right, so it's a more application for multiplication, but the idea of a transpose that basically you will see it in your class in this context. It's seen a lot in this context. Now the transpose has its own property as well. And let's see some of the property of the transpose of a matrix. So everything has its own properties. So property of the transpose. The first property is, suppose I take a matrix and I transpose it. And then I get something and I transpose it back. All right, what do you think I'm gonna get? Just build an example in your head and see what's gonna happen. What do you think I'm gonna get? Let's see what those two operations. I take a matrix, 1, 2, 3, 4, 5, 6. That's my matrix, exactly. When I transpose it, what am I doing? Those will become the column. Now I have a new matrix. I transpose my new matrix, means now I'm gonna undo what I did. The rows are gonna be con. The rows are gonna be a con. So this will take me to my original matrix A. Okay. Now another one property that is a bit hard to prove, but you should know it, is that if you multiply two matrices and you transpose them, what should we get? What we shouldn't get, and then what we get, what we should not get. So let me tell you by what we shouldn't get and then what we should. If suppose we have A times B and you transpose, so our natural inclination, that's the natural inclination, is to write this. That's our natural inclination. And let's see that if our natural inclination makes sense. All right, suppose A is 2 by 3 and B is 3 by 4. A times B will be 2 times 4. So the transpose is 4 times 2. So this should be a 4 times 2. Now what's the problem? If I go here, A transpose is 3 times 2. B transpose is 4 times 3. This is not even defined. So our natural tendency totally fail. That's a simple reason why it fails, even though the product doesn't work. What work actually, but the proof is not trivial, that's why I will not, is you have to flip them. So it's the transpose of B times the transpose of A. So that's how it acts under transpose. Okay. Now, the last idea we're gonna talk about today for the last 10 minutes is we defined multiplication, how we multiply, and that's how we will multiply by hands. That's the way it goes. There is an equivalent definition for multiplication. It's a little bit more theoretical, but we should definitely know it and we will work with it. So an equivalent definition of multiplication. Definition of the product of two matrices. Multiplication or product of two matrices. Equivalent, it means the same, give us the same numbers, but it's a little bit written differently. Okay, let's see what this one says. So I'm gonna go back to a matrix A, and I'm gonna multiply it by another matrix B. But this time there is something I'm gonna emphasize in that. So suppose this is my matrix A. 1, 2, 3, 4, minus 1 is 2. That's my A. And I'm going to multiply it by B. So B has to have here 2. So I'm going to put for 2. I need, I don't know, 5, 6, minus 1, 7. It doesn't really matter as long as my rows coincide with the number of columns B. Okay. Now what I'm going to, in computing, I only want to compute the term that comes here. I'm not going to worry about anything else, only those terms. Okay, how do I get this term? This row, this column. That's how I get it. So it's 4 plus 4. How do I get that term? Row, column, 12 plus 8, 20. How do I get here? Row, con, minus 4 plus 4. okay? And the rest I'm not gonna worry about. That's the only one I'm gonna worry about. But if we watch very carefully, if let me see, I call this here, I call this the vector B1. Okay, I'm gonna give it a name. I'm gonna call this the vector B1. What is this vector here? If we remember, a matrix times a vector, how do we do it? There are two definitions. One is a linear combination of the columns of A, which give it meaning. The second, the more computational, is the row column. So what I'm getting here is basically like taking the matrix A and multiplying it by the vector B1. So that's the actually theoretical definition. Okay, sorry. So it's A times the vector B1. That's what I'm getting here. Right here, again, I can think about this in the same way. Right here, what I should get is like A times the vector B2. Because if I multiply, it's like taking this matrix A and multiplying it by B2. That's the entries, because what does it mean? Row, column, row, column, row, column. And this row here is also A times the vector B3, where B3 is this vector. So I'm really multiplying the natural way. What I'm doing now is emphasizing the column structure of the matrix B. And if I emphasize this column structure, then multiplying them is like taking the A, B1, A, B2, A, B3. So this leads us to the following theorem that tells me so we have the following now. So you can call it the theorem, we can call it whatever we want. So suppose A is in M by N, B N by S. So I want the product to be defined. And I want to emphasize the columns of A. So assume that B is the following. B1, that's the first column, B2, etc. And what should be the last column? If B is N by S, it means this one here has to have, we have S columns right there. Then A times B. It means A times B1, B2. So those are the columns. I'm emphasizing the column structure of B. This is equal to. So this tells me that this is, we can almost distribute the A with respect to the column vector. It means this is going to give me A, B1. That's the first column of the product. A, B2, the second column of the product, and so on. So A, Bj, which give me the jth column of the product, and so on and so forth till the last one. So in other words, in a written word, it means that if I'm going to emphasize the jth column of the product, this one. So the jth column of AB is equal to A times, I multiply A by the jth column of B. Okay, so the jth column of the product is the same thing as taking the matrix A and multiply it by the jth column of the matrix B. So a very quick application so you understand what I am talking about in this problem. So very quickly, suppose I take the following matrix. Okay, so this is the picture. And suppose I take A to be whatever, 1, 2, 3, 4, 5, 6. And B is whatever B. So I can put a bunch of numbers here. 1, 1, 2, 2, 1, 4, 3, 0, 2. It doesn't matter how many columns I have. I know that the product is defined. And let me make up some stuff in here. -1, 3. Okay. And now the question is, find the third column of AB by using the idea that we just developed. I know that you can find it without it, but now I want to use the idea that we developed, the third column of AB. Or I can rephrase this question, write the third column as the product of a matrix and a vector. So I can rephrase it as write the third column of AB as a product of a matrix and a vector. So what's the third column of AB? So this tells me that the third column of AB, of the product.
We can't see it.
Oh, thank you very much. Is equal to, so that's B1, B2, B3, B4. So the third column of AB is A times the third column of B. If I call this B1, B2, B4, it's A times B3. So if I ask you to write the third columns as the product of a matrix and the vector, that's the matrix and that's the vector. That's really what the idea is. And now multiplying them is not really the big deal. The big deal is basically to understand what's really going on here. That's how we can pick up the third column, and that's how I can write it. So the rest is I just basically put C302 here, and sorry, 1, 2, 3, 4, 5, 6, and I can just multiply. And always we have to focus. Whenever you multiply, ask yourself, what should I get? What type of vector I get? In this case, I have a 2 by 3, 3 by 1. So I should get a 2 by 1. So always ask yourself, what shall I get? What kind of matrix I get when I multiply? So when I get 3, 0, 6, 12, 0, 12, 24. Okay. So now the idea here is to find the third column. What is the third column of the product? It's the matrix A times the third column of B. So that's really what it is. The last thing, give me 2 minutes because I want to finalize section 2.1, is about the power of a matrix. Okay. It means, suppose A n by n. Okay, and if you're writing, leave an empty spot here for a reason. Power of a matrix, it means sometimes we see A squared. What do we mean by A squared? We mean what we want to mean. We're not changing the meaning. It's A times A. But when will this make sense? To be able to multiply A by itself. Under what condition can we do it? Finish my sentence. No. I don't know what you mean by that. Right. If M and N are equal. Why? Absolutely. So we cannot multiply, we cannot take a power of one matrix unless this matrix have the same number of rows and the same number of columns. Now let us see why. If this is M by N, now I want to multiply it by A, and I want this to make sense. Those has to be equal. Otherwise, it doesn't make sense whatsoever. So it's defined if M equal to N. So now I can talk about the power of a matrix. So if we have a matrix, the number of rows, so now I can change. So if A is N by N, so it's if a matrix is, and we call those square matrix, if A is N by N, now I am fairly comfortable with that, then A square is what you want it to be, A times A. A cube is A times A times A. And now the whole product is actually defined. Okay, so we can talk about power of a matrix, but to be able to do that, we have to make sure that, things make sense, things matches. All right, sorry for taking 4 more minutes extra. That's it for today. Please do the homework for Wednesday. Okay, and the exam, I know it's going to be a while. I plan to grade them over the fall break. So you will have them sometimes during the break. I know that you're curious about them. Okay, so time is up. If anybody has any questions, you can stay and ask. Anybody has any questions? Okay, so see you next time then.